because it's non-renormalizable theory.
You can see the you can see my screen.
Yes.
All right. So let's start with your question. It's an important question, of course. And really, the way I said it yesterday, sort of, I said I'm going to ignore it. Well, what it means that when I say that I'm going to ignore it, I mean I'm not going to talk about it. I can never ignore gravity, you know. If I ignore gravity, I wouldn't be here talking to you. So you and I, of course, have to live with gravity. The reason why it wouldn't make sense to speak about gravity really wouldn't make sense. Imagine that I mean, where did I finish yesterday? Okay, I can start the lecture with your questions. So we finished yesterday, we said QED, right? There were sort of, we said when all the dust settles at the end, what Feynman taught me when I will compute scatterings, all I have to know really are the propagators, well, the final states and so on. And we remember yesterday we said if there is a fermion scattering, we have a photon propagator, which goes as 1 over q squared. Which then becomes 1 over r as a static potential. And of course there is alpha, so I should write alpha over r. This is electromagnetic force. And then we said gravity by analogy. We know by looking at the potential, analogous potential would be G Newton. Mass is m1, m2r. This is gravity. And then we said, because G Newton is so weak, 1 over m Planck squared. M Planck is 10 to the 19 GeV. Planck, let's write. The force is very weak. We said that the gravitational potential divided by the electromagnetic potential is some number of 10 to the minus 36. Now, what would we mean that I include that? When I study physical processes in nature, not only here, as in the old days when Q is very small, we have reached the situation when Q is maybe today, you know, even TV today, even maybe 10 TV. It's called LHC. So compute these effects in the standard model that we will be talking about, which are on the order 1 over q squared alpha. And then I have to start doing perturbation theory. That, of course, is just the leading term. We said that we will be expanding in alpha, so there will be something of order alpha and of order alpha square and so on, and alpha cube and so on. These effects, sorry, this should be alpha. This should be alpha, this should be alpha square. These effects, of course, are of order 1 over 100. And this is what we are doing today. We are doing high precision study of the standard model. We are actually going beyond even 1 over 100. Today, the standard model is studied with a precision of 10 to the minus 3 precision. We are getting there. And I'm saying that I will include the effect, which is 10 to the 33 orders, 36 orders of magnitude smaller. How could it make sense? I would have first to sum all the, I don't know, 30 orders of expansion to get here. There is a consistency when you compute things. It is crazy to compute the effect, which is 36 orders of magnitude, when you're just learning how to compute something which is 1,000 times smaller. Unless two things. So in order to study gravity, two things will be needed, unless you have a new phenomenon which standard model gives 0. Then, of course, you are saying, well, if it is 0 because of some reason, then maybe I should study then something that comes out from gravity. The standard model, but I'm saying without gravity gives zero. When we found things that are zero, then we can look at the connection. But of course, then I need, however, at the same time, I need the experimental capacity for one way or other to study such small effects of order 10 to the minus 36, okay? This is an extraordinary thing. So even if I find this new phenomenon, we can talk about that towards the end of the standard model. It's very hard to find something coming from gravity. I will show you how it could come from grand unification, very tiny effects that we decided to probe because we developed experimental capacity to probe those effects. Two miracles are needed. Then we'll talk about gravity. So remind me when we come towards the end of the standard model to rethink about this. But at the moment when I'm studying the processes which are present in the standard model, electron scattering on the electron, neutrino scattering on the electron that we'll talk about, then it just doesn't make no sense that I do the things. And not just because the gravity is an effective theory, renormalizable, not renormalizable. It's just too early to talk. I told you yesterday something interesting, or on Saturday. I don't remember. There is this extraordinary thing, Newton. Okay? The father of it all. This is the one moment that defines science, modern science. It's called Newton. It starts with Galileo, and then all the difference in the world starts with Newton. Centuries later, we still can be in awe of the unreal things that he has done. So he says, only a fool, says Newton, can think that forces are instantaneous. But, he says, I have no means of describing gravity messenger. So I will pretend that gravity acts at distance. He will pretend he's a scientist. This is the beginning of modern science. This is why Newton calls physics natural philosophy. Newton says physics is natural philosophy. You can be as philosophical as you wish. You can be deep, you can be profound. I use these words all the time. The last great physicist who would speak a lot about natural philosophy, Steven Weinberg, he often used this expression, emphasizing that he started studying philosophy. So he had this philosophical trait in him. I tend to have this in me, but it's all irrelevant unless you're describing natural phenomena. Then you're not a physicist, okay? So when I speak of physics, and you should speak of physics in that sense, we should speak in the physics, not in the sense of Democritus, but in the sense of Newton. So, and I'll give you the illustration, similar illustration. In a few minutes, I'll say something which is very similar to Newton. That will come there. So this is the thing that we do. Until I have something to say about gravity, I will be silent. We should not speak of something that we have no means of probing. What we can do, meanwhile, by the way, we can work trying to understand more deeply gravity as a quantum theory, that's for sure. But when I'm giving a phenomenological course, then I have to stick to the phenomenon of nature. Did I answer it? What you? This should be the guiding principle throughout the course. I'm only ignoring it because the effects are tiny. As soon as someone tells me that there is a way of measuring these tiny effects, I change the standard model course immediately. But you're right, strictly speaking, gravity is a part of the standard model. That is a force in nature. Standard models should describe all forces. Okay, look, we'll come to an even maybe nicer example from our point of view from Newton, okay? And this is the following. Look, we stop here. So we got electromagnetic force that goes as 1 over q squared, effective interaction. In other words, I can write, if you wish, the effective Hamiltonian of QED as we could write it as alpha over q squared f bar gamma mu f. Actually can be two different fermions, but symmetrically, you agree, something like this. This is the exchange of the photon propagator. Photon couples at every vertex, there is f bar gamma mu f. Here at the vertex, I will have f bar gamma mu f with a coefficient e. And the charge that I took of order 1, this is an estimate, okay? Alpha over q squared, f bar gamma mu f squared, schematically written. And so let's go back to let's go back all the way back, even before the QED is developed in the late 40s and 50s as a normalizable quantum field theory. Let's go to the 30s. Let's step back in time. We'll do that from time to time. It will be very useful. Because what happens around that time, the clear picture of beta decay has emerged. It started with, let me remind you, I'm sure you all know that. So we are now coming 30s. Why the 30s are so important? The birth of weak interactions. It starts with a neutron. Actually, it's a nuclear decay, but effectively neutron decaying into proton from the electron. And something was missing. Remember what was missing when neutron was decaying into proton, the electron? In this case, you would expect the electron energy. If this is the distribution, you would expect the electron energy as line. This will be the energy of the electron. And this is the, let's say, probability of having electrons emerging from the process. It was not a line. I'm making this very small. This is very familiar. It was a curve. What happens in 1930? Pauli writes a postcard which changes history forever. Look what I'm telling you these days, how serious those people were and how responsible. Pauli doesn't write a paper because he's not sure that this can work. If you read his postcard, it's very interesting. There is a radiative congress that he's not attending. He's not attending, which is a very important Christmas dance. He has to be present there. But he's desperately thinking of saving the physics of beta decay. Electrons were not clearly identified. It was called beta radiation. And he says, maybe there is another particle. Forgive me, he says, my dear colleagues, for saying this desperate thing. Imagine he's suggesting one particle and he's scared to write a paper because he could be wrong. Today, we actually call this anti-neutrino because it always comes together. So we gave it a name, anti-neutrino. That's our privilege, because this way, the lepton number that I'll mention in a moment is conserved. This way, of course, if there is a yet another particle, he gave it a name neutron, as you know. There was no neutron in 1930. Neutron is discovered in 1932, if you remember, Chadwick. So he calls this neutron. And a few days later, the Rome group of Fermi and collaborators will give it the name of neutrino, a small neutron, right? This is how it all starts. This is 1930, by the way. It started already at that time, this extraordinary weight that particle physics requires from us. Very soon, Pauli will repent. He will have a remorse for suggesting neutrino because of the following. You all know, of course, you went through Alexei's course. So comes Fermi a few days later and writes a theory of this process. And Fermi says, what Fermi says? Fermi says, look, there is this effective Hamiltonian of QED, says Fermi. And I know that there is a particle called photon that I can take as an exchange, but I'm going to look at the effective theory. I'm sure, says Fermi. Fermi says again, there could be a messenger, there should be a messenger. And you know what the messenger is, right? There is a messenger, we call it a W boson. We'll come to it. But says, I have no way of describing coherently the physics of the messenger, says Fermi. So Fermi says, I will pretend there is no messenger. In order to write a verifiable law of nature, I will do what is called today an effective theory. I pretend no W, and I will do an effective theory. He says, if I don't have a way of describing, I can speculate forever. But if you cannot test, and I don't have a theory of that, the right approach is to use the effective theory the way Newton did some centuries before me. Okay, this is an extraordinarily important step. This is the beginning of modern approach in particle physics that we follow to this day. If you don't have a theory, start with the effective one. We'll understand throughout the course what I mean by the effective, but it's similar to this one. Here I have integrated photon out. There was a photon propagating. There was an interaction with the photon, but I just propagated it out. We say integrated out, and I got something that forgets about the origin of the, says by same analogy, I will write effective theory called Fermi theory. This is called the Fermi theory of weak interaction. That's what Fermi does, which is, he'll write it. It has a strength which is G Fermi over square root of 2, normally defined. I don't know why I put square root of 2. No, this doesn't make sense because I haven't yet precisely defined my interaction. What he does, he says there will be something, let's say, schematically, G Fermi. And then he says, by analogy, he says, he wrote, very simple, something similar, F bar, gamma mu F squared. We're really here, well, I should be more precise. I'm sorry, I shouldn't write like this. I should be more careful here because it's not just the scattering. I should write P bar, gamma mu N, entered, proton came out, electron entered, electron goes out, anti-neutrino goes out, which is the same as neutrino entering. Remember, particle goes out, equivalent, antiparticle goes in. Particle P. That's what Feynman means by his Feynman diagrams. Antiproton goes in. So he writes an effective interaction with complete analogy. Okay, in other words, by the way, when I call this anti-neutrino, let me just remind you, I am defining that the neutrino has a lepton number, which is the same as the lepton number of the electron, which I will call 1. With this definition that what comes out is anti-neutrino, I have the right to introduce the lepton number. A neutrino is a lepton, just like electron. From the weak interaction point of view, there is no difference between neutrino and electron. Yeah, exactly the same particles. Okay, photon knows that the electron is different from neutrino because the charge of neutrino is 0. And by the way, the charge of neutrino is 0 because of the fact that the charge of the proton plus the charge of the electron is less than about 10 to the minus 40. This is an extraordinary thing that emerges from neutrality of our universe, which you and I will read that Q proton is actually minus Q electron, which will be +1 for us. I will show you later, but I won't be able to teach it, but I will show you how actually standard model predicts that. It requires that theoretically, structurally. But anyway, to extraordinary prediction, we can assume that proton is positively charged if electron is negatively charged. Which means that neutrino has charge 0 with a precision of less than about 10 to the minus 40. Charge conservation. Charge is conserved to an extraordinary precision. Okay. Now, what is G Fermi? G Fermi must be 1 over the momentum square. Remember, it's 1 over Q square, and it has a certain strength. I could call it 1 over lambda Fermi square. People often do that, and it must be inverse mass square, and it turns out to be 10 to the minus 5 GeV to the minus 2, which is 10 to the minus 5 and proton to the minus 2. This is the and this is why they decided to call the weak interaction weaks. The reason was why this is weak. This cannot be weak because it's a dimensionful number. This is not small. Okay, nothing weak about this. This is very important. I know that you probably know this. Nothing weak here. The reason it's weak here, that the experiment at the time was done at the momentum much smaller than GeV. They were still doing MEV basically. Okay, it will grow with time, but much smaller than MEV. In other words, in this sense, now weak over electromagnetic becomes this extraordinary small number of order 10 to the minus 5 or smaller. This why now I'm allowed to call it a weak interaction. And it turns out that the reason why Pauli regretted introducing the neutrino, it's amazing how conservative these people were. Well, because your reputation depended on being right, as I keep telling you, you know, that was an era when physics was taken seriously. And it will take a long time before neutrino is found. Someone knows when. When was neutrino discovered? Common and Reines. Neutrino discovery. Roughly. I know it's an ancient history for you guys, 50, but still.
56, 56.
Great, 56 precisely. 56, they had the results even a little earlier. By 1956, they write this famous telegram to Pauli, telling him, we found it. Okay, telegram to Pauli. They will write the paper in Physical VOD, okay. There is a telegram to Pauli, famous. They found the neutrino. This we should call, you know, amazing the time, 26 years. Meanwhile, Pauli regretted introducing neutrino and even asked to be forgiven. Now, all of a sudden, when they discover it, Pauli becomes very wise. So Pauli says, I will often cite this, or let me write it down. Everything comes to him. Let me put it here. We should say here, but there was no here at the time. There was only him. It was a macho society, and there were also very few women. You know, you can count them on. Well, there were basically no women. To him, her, who knows how to wait. It's actually not fair what he writes, because he didn't know how to wait. He said that neutrino will never be found. It's easy to be wise a posteriori, okay? Now, why was Pauli so pessimistic? Because if neutrino has only weak interaction, it's neutral. What else can it have but weak interaction? It has gravitational interaction, but that's even smaller. So what he says, of course, if neutrino is only weak interaction, then you can easily compute for example, you can compute the mean free path of neutrino. So you take the energy of MEV. Imagine you're producing neutrinos with the energy of MEV. Let's talk about that in a second. Do you know what the mean free path of neutrino is with this energy? Mean free path. It's the distance you travel before interacting. I don't know what is yours. Mine is around, roughly around on the scale of a meter. It's like 20 centimeters. I'm riding close to my window, a meter or two there, on the other a meter before interacting. So, for example, lambda Goran, let's say, is about a meter. Do you know electron mean free path, roughly, without energy? Is it smaller or bigger than mine, electrons mean free path? It's actually smaller. It's less than a centimeter. What about lambda neutrino with this energy? You got to have a feeling for this. You should never be allowed to speak of anything that you do, whether it's called ADS, CFT, grand unification, standard model, because you know you may be in a party and someone may ask you, tell them I'm a particle physicist. He said, I heard about neutrinos. What's their mean free path? I heard they don't like to interact. There are a few numbers that I'll ask you to know. Give me just roughly. Someone should try. Just try it, okay? Don't feel bad. I need an answer.
1 kilometer.
Yeah.
More? Some other try? It's bigger than a kilometer. You know, there is always a joke when the student on the exam and you ask them, you say, oh, it's very big. Really? Very big? What do you mean, how big? Oh, very, very big. How big? Extremely big. You know, we like to, but you don't know. It's bigger than this. And it's so much bigger that it's a kilometer. It wouldn't be a weakly interacting particle. The physics of neutrinos, and which is the neutrino is the protagonist of the standard model. We have to keep neutrino in mind all the time, okay? Because we are now going to talk about weak interactions, and it's crucial to have the understanding of neutrino. I have someone here telling me that they are interested in neutrinos. What does it mean that you are interested in neutrinos? You have no idea. I need more. Just try one more number and I'll tell you. Yes? No? Okay, I'll say it. It's 10 to the 18 centimeters. I like to say it in centimeters. I'm sorry. I know everything in centimeters. Do you understand how big it is? It's a million times bigger, almost, than the distance between us and the sun. Neutrinos practically do not interact with anybody. And this is why Pauli, when he realized that, this was computed by Bethe and someone, I think very soon, and then Pauli gave up on the possibility to observe them. And it seems impossible, of course, that we'll observe a particle. You see, neutrino is crazy. It's completely aloof. This is strictly speaking, neutrino basically doesn't interact with anybody. I can increase it if I increase the energy, as you know, because the bigger the energy, the more likely it will interact. Of course, it's not just the cross section. Anyway, so this is a feeling for the weakness of neutrino interaction. So how could they observe neutrino? I'm sorry that I asked you this basic question. I should move along, but I just want to see how much you remember from the particle physics course. How can you see a particle that doesn't interact with anybody? This is a very similar question that you may hear that.
We try to see the inverse beta decay.
Right, but how can you see what I'm saying? How do you see something that is so rare? How did they see what did Cowan and Reines do? What was the experiment at the time? Which were the neutrinos they were looking at? Reactor neutrinos. This is what Cowan and Reines did. By the way, the idea came already before. The name that will come up from time to time when I speak of neutrinos is Pontecorvo, a great Italian physicist. But Cowan and Reines independently, he talked about it earlier, decided to look at the why, because you produce a lot of neutrinos here. The flux that they had was about 10 to the 13 neutrinos per centimeter square per second. You know, as you know, it's winning a lottery. Probability is small, but if each of us buy a ticket, you know, together we boost. So you can overcome small effects by looking at the coherent phenomenon. Okay. The rest is history. This is 1934, more or less, when he develops the theory Fermi. Roughly, I may not remember precisely. I just want to give a rough feeling for history, okay? Just to sort of see that it takes a long time, which is similar for us. The idea is that my generation worked on, developed, the generation that came after Weinberg, Lesher, Salam, and those, the things that we worked on and developed, some of us and some others, which were like 70s, are only now being proved because of the LHC. We had to wait more than 30 years, okay? But they already had to wait. The crazy thing is that these Cowan and Reines had to wait so long to get the Nobel Prize that Cowan died and Reines was almost 90, okay? One of the most important experiments in modern physics done in the 50s. The Nobel Prize was given in the 90s, completely insane. But anyway, what emerged? There will be one more crucial step here. Now the time goes on. The next moment, which I just want to mention in the history of particle physics leading to the standard model, is parity violation. This is crucial. You remember roughly when parity violation was suggested and observed? Just to have you participate a little bit, to help me.
It's around 70s, as far as I remember.
No, it couldn't be. How could it be around the 70s? When was the standard models developed? You have some idea when Lesher wrote his paper? I'll help you here. Just where should I write? I should have started with that. Look, let me write it here. Let me write it here, okay? Just to have, when I speak of the standard model, so anyway, I need that. This is lecture 2. To send you these notes. Lecture 2. Let me just have it here. The standard model, the electroweak part, it starts with the work of Glashow, who suggests the SU2 cross U1 theory. You know roughly what time?
1950 something.
1961.
Oh.
No, it couldn't be before Reines. It cannot be before discovery of neutrinos. Think about that. I need to know that there is a neutrino in order to develop a theory about neutrinos to take it serious. You have some idea when Weinberg and Salam wrote? Well, Salam never wrote a paper. He published a talk. So a particularly important moment, okay, is Weinberg's paper, which is beautiful, easily to read. I'll suggest you strongly to read Weinberg's paper, okay? You don't need to read Glashow's paper. But you should read it just to understand how hard it was for him. When you start, you are confused. And that paper is hard to read because it's all unclear. 1967. In 1968 is Salam, with analogous idea of so it has to be between them, and this is fantastic. This year 1956 is incredible. Parity violation is in 1956, and this is who? Do you remember the people that suggested it? I just want to see that some little feeling of history you should have, because this is one of the most important pages in the history of physics in general.
There was the Wu's experiment.
Right. Experiment is Wu, but who writes the paper?
Lee and Young.
Lee and Yang. This is amazing. It was one of the greatest bombshells in science. In the summer of 1956, they suggest that parity is violated. In the winter of 1956, Wu experiment. It's still 1956 at the end of the year. And Lederman does a similar experiment, but different. It's also 1956. Lederman and Garvin. I don't know who else was an experiment. Maybe they were the only well-known. Also 1956. Parity violation is confirmed. And not only that parity is violated, you know, the prejudice that the parity must be conserved was so big that in 1957, they got the Nobel Prize immediately in 1957. You should look at the pictures of Lee and Yang in 1957. They look, you know, your age. And they were just a little older. It's a real bombshell, just like Dirac's bombshell. You know, I will keep telling you the modern particle physics starts with Dirac antiparticle. A fundamental moment is the Fermi theory of weak interactions. Parity violation plays a profound role, and it's maximal. Parity violation is maximal. What I mean by that, I look at some nucleus. It was cobalt-60, I think. And I polarize it, say with a spin up in this direction, so I can have a direction. In the parity conserving world, you would expect the electron going up, anti-neutrino going down. And half of the time, you would expect the electron going down and anti-neutrino going up. One of the two doesn't happen at all. Parity violation is maximal. To this day, the world behaves as if there is only left. Call one direction left, call this left. The right wouldn't be there. It will take a year for Marshak and Sudarshan. The next great step is the V-A theory of weak interactions. There is a beautiful talk by Weinberg about 10 years ago, which is called V-A was the key. It's worth reading. He writes very nicely, Weinberg as usual. You can find it on archive. It's really a crucial, very important to understand that, okay, without this, neither Glashow nor the others would have developed the theory. But especially Weinberg and Salam's, the Higgs mechanism, introduced in the standard model. And they analyze all the experiments. So this is Marshak and Sudarshan. It took a year only, extraordinary. 50s and 60s, by the way, 50s are the development of QED is terminated. Now we have the discovery of neutrino, discovery of parity violation, the V-A theory. There is also a paper, not as complete, but around the same time by Feynman and Gell-Mann. Okay, Gell-Mann should go first, I guess. And no, Feynman and Gell-Mann, sorry, it goes like this. This is 57. And the conclusion is that the effective theory of weak interactions, or beta decay, if you wish here, looks like G Fermi over 4 square root of 2, no, 4 G Fermi over square root of 2 PL bar gamma mu NL EL bar. I'm writing the proton, it's really the quarks. We'll start talking about the quarks, just a little amusing history. Everybody appearing here is left-handed, only left-handed fermions. Maximal violation of parity. In a conserving world, you will have both left and right, as in QED. But here only left. This is a crucial step that you know and you've been told, but I will be emphasizing. Okay. Continues. Any question here while I am just reminding you of history? Well, I'm doing a little more. It seems that maybe some of the things can escape, but I'd like to feel that I may be saying something useful and not just reminding you. Okay. How we would understand the parity violation, but let's come to it. I can postpone it a little bit. What is happening now in the late 50s? Slowly, oh, no, not slowly. In 1957, Schwinger, this is a very important, one of the fathers of QED, starts with an idea which he doesn't formulate coherently, of a gauge theory of weak interactions. Now, why would this idea emerge? The crucial thing that you will be learning in your field theory course, or maybe you learned, I don't know which stage are you in the field theory course. When did you start the field theory course?
In the field theory course, we have covered Young-Mills theory.
Aha, so you know that QED is a normalizable theory.
Yes.
You know that.
Yes.
And it's normalizable precisely because of gauge invariance. It plays a profound role. Let's put it this way. Well, we can think of the nitty-gritty of that. Let's come back to that. The gauge principle worked very beautifully to make QED. So in other words, at that time, QED is a normalizable theory. Now, this fancy word, normalizable, it's a fancy word to say really what I mean, that it's a good theory. I can compute. I should have said good theory. In other words, the scatterings, when I compute the scattering, the amplitude is finite. I don't get infinities, which I could get, because when I do perturbation theory, in most any theory except for some small class that we call renormalizable, you get infinities, okay? And it works, the theory. So, you know, the people start thinking, oh, maybe, Schwinger says, maybe here, I could try to imitate QED, including weak interactions. It's very interesting. This idea is fantastic. It will revolutionize physics, okay? It's a crowning achievement of 20th century physics, okay? But interestingly enough, this genius, it's sort of, he has a very good student, and instead of developing himself, that maybe he could have, he gives to his student, the student name is Gleshow, starts working in 1957. He will write the thesis in 1960. He's working for some years, couple of years, developing the gauge theory of weak interactions. Actually, electroweak interactions, we'll see. I should have said really electroweak, because Schwinger gets an idea that it would be beautiful to unify electric and weak interactions. Now, in order to develop a gauge theory, you realize the following, that in QED, 1 over Q squared of QED, it comes with the exchange of a gauge boson, the photon, which couples to the current. So if I want to reproduce the G Fermi, the theory, I need the messenger that couples, let's say, neutrino becoming an electron. That's what is happening. Well, the electron becoming a neutrino. Such a gauge boson, by the analogy with the photon, well, the interaction has to be left-handed. We just learned. Marshak and Sadroshan and Feynman and Gell-Mann, but especially Marshak and Sadroshan, who realized the experiment. There is a coupling E here. Here there is a gauge boson that we call W mu. What is the difference between the photon and the W? They're almost the same, but there is one profound difference.
The mass.
Sorry?
W is massive.
Okay. Even more important, well, maybe I'm not fair, charge. So I should write W plus, and the coupling I will call G over square root of 2. There is some reason that it's G over square 2, you will understand later. At this point, just historic. This idea, of course, is obvious, that if I believe that there is a messenger, I get immediately the picture of that. And whereas the photon mass seems to be 0, it's very tiny, the W mass is on the order, we know, it has to be on the order of 100 GeV. Because when I exchange it, in other words, why? Because G Fermi then is going to be roughly G squared. At every vertex there will be G over MW squared. Actually, from the propagator, you get MW squared and Q squared, but Q is very small. So roughly we get this. So MW is roughly on the order of 100 GeV. This will take, we'll talk a lot about this. Okay, please, this is schematic. I wanna do this later much coherently, but what I want to start immediately is to give you a flavor today of what would be required from a theory, a gauge series of weak interactions. We will have to fill in the gaps as we go along. And I think this could be a good moment. Let me see first if there are questions here. This we have to justify, by the way. This should be, we will justify this by getting the massive propagator. Oh, tell me please, did you in the particle physics course, did you compute the massive propagator? Or did you write it down? Do you remember? Yes or no? Hello?
Did you mean just 1 over q square minus m square, something like that? Or-
Well, whatever, right? It's the form is very important. It's not just, you know, there is a tensorial form. I'm asking what would be the form of the W propagator? Do you know this? It has minus I, okay, let me write that, q square minus mw square, strictly speaking. Then there is a tensorial form. Did you derive that or wrote it?
Is it G mu nu minus P mu P nu over P square over G P square M square? M square.
No, m square. Was it written before? Did you ever see this? Is this new for you?
No, no.
Everybody knows this? Tell me better, please. Are there among you those that have never seen this before? For whom it is new?
It is new for me.
Okay. Even if there is one person, I don't want to leave you with a whole, we'll do it. Maybe we'll even make it a homework, but we will of course outline how it goes. Okay, very good. Look, it's 11:54, so let's take our usual little break we'll be having. Let's get back in like 6 minutes. I need you fresh in what I will be talking about. Okay, it's 12 o'clock. Any questions, please? By the way, for the sake of argument that I used before, the precise form of the propagator is irrelevant. As long as the Q is much smaller than MW, you know, whatever the details are, the propagator will look at the 1 over MW squared. But we will do this from tomorrow. We'll get precise and organized. Today is the illustration. I want to give you a flavor. I want to whet your imagination. I want to show you today how the standard model started to be born, so that you know where we are going, what we have, what is the task that lies ahead. So Glesher has a PhD assignment to develop the gauge theory of weak and electromagnetic interactions. And when you have a new idea, a new theory to develop, what you always do is, of course, the minimal theory in order to make predictions. This is what is always done in every page of the development of history of physics. The history of the development of physics, whether it's Newton or Einstein or Maxwell. If you think of Einstein, it's the minimal Lagrangian that you write with those principles. So what is the minimal theory? What it means is the minimal gauge group. What is the minimal gauge group that could unify, that could have weak interactions and electromagnetic, but even just by weak? Someone wants to say?
SU2.
SU2 cannot be smaller than SU2. You see, because now we know we are trying to develop the theory in which there are 3 generators, W plus, W minus, and the photon. But even if I just thought of W plus and W minus, or you could say, why don't you try U1 times U1? I don't know, if you want the photon, also U1. No, this cannot work, because U1 means messenger is neutral. We saw it, you know that messenger is neutral, but W is charged. So the minimal gauge group, thank you, is the G minimal, is SU2. Very good. SU2, of course, means that I have, if I speak of a field psi that will develop phi, this must be a doublet now. That's the minimal representation of SU2. For example, a typical doublet would be neutrino and electron. You agree? They are together because under weak interactions, neutrino becomes electron, electron becomes neutrino, so this will be the doublet. So this you could call psi. And I will often call it L, leptonic, to emphasize this is a leptonic doublet. What it means that psi goes into U psi, so that U dagger U is 1, of course. And SU2 is determinant 1, determinant is 1, so I can write U as e to the I Hermitian, as long as 2 things, H is H dagger, so that is unitary, and trace of H, of course, is 0. That will ensure that the determinant is 0, but that means that H I can expand in the basis that the basis is called Pauli matrices. Why don't I write in general TA, where TA are Hermitian and traceless, obviously, just like H, and A goes from 1 to 3. There must be 3 of them because they are traceless, not 4. There would be if they were not traceless. And TA, as you know, are the celebrated Pauli matrices normalized so that, sorry, and what I want to write is this, TA is sigma A over 2, this you know. As we go along, I may remind you some of the basics of the, please, the crux of gauge theory is the group theory. The crux of group theory is SU2. If you learn SU2, you know everything, including the Lorentz group. It's all in SU2. And I will be showing you amply during the course. So that, of course, they satisfy commutation relations, the celebrated notations of Pauli matrices, or SU2 in general, epsilon ABC, TC, where epsilon ABC is the anti-symmetric tensor, as you know. This is what I mean by SU2, of course, this you know. So there are 3 generators. And one of them, T3, this is diagonal by convention, right? Sigma 3. We say that the rank of SU2 is 1. The rank is a number of mutually diagonalizable operators. There is just the generator is just 1. These are matrices that form Cartan subalgebra, as you know, is sigma 3, which implies immediately an extraordinary prediction. Look at this, and this is beautiful. If the theory was based on SU2, this is the problem that Gleshow faces, and he works on this for years. He will fail, and he will write a thesis summarizing his failure in 1960, because what you Q electromagnetic must be then proportional to T3, which I'll take the constant of proportionality 1 just to illustrate the point, but it could be even if I put some constant here, I will have immediate prediction that trace of, you see what I mean when I say SU2? That means that you live inside SU2. So charge cannot be now outside because you decided that everything is inside SU2. Which means that the trace of Q, well, even before writing this, that the trace of Q electromagnetic is 0. Which is another way of saying that charge is quantized, you know, just like spin, remember? The non-abelian groups have a beautiful property that is seen in SU2 first, that the charge in question, okay, if it's spin, it's quantized. Or if you wish, this implies that electromagnetic charge is an integer times the minimal charge. Which is a beautiful prediction because this is actually what happens in nature. This is one of the greatest miracles that this day is sort of fascinating as physicists, okay? And that's the fact that really instead of proton or neutron, I should have, of course, have spoken about up and down quark, right? Proton is UUD, neutron is UDD, which from here, as we know, Q up is 2/3 and Q down is -1/3 and Q electron is -1. And I don't know, there are other generation, of course, and this incredible thing is a fact of nature. In nature, charges are quantized. All charges, all that we have observed, Q electromagnetic in nature, experiment, observation, is proportional to n times, say, the smallest charge is the charge of the down quark. By the way, we often say that there are fractional charges. This is just a funny language because we started with electron to be -1. There are no fractional charges. All charges are integers of the minimal charge, which is charge of the down quark. It's just because we started with this that it looks fractional. But the logical, had the down quark been observed before the electron, then you would have said, oh, then I would call this -1 and the charge of the electron would be -3. So by charge quantization, I mean this extraordinary ratio between electron, which you must admit is an extraordinary miracle. And in nature, this is observed with a precision in less than 10 to the -20. Imagine that our masses, which are randomly distributed, are integers times the. So this extraordinary effect of nature would be actually naturally explained. However, this is wrong, unfortunately, because in SU2, you see, it will tell you, if you take the Q is T3, in the minimum normalization, you will find out immediately that the charges are plus or minus half. All of the doublets are the same in SU2. They will not be distinguished. So in other words, one doublet would be up and down quark. The other doublet would be neutrino and electron. This is what the weak interaction will do. And all their charges would be, so this fails. This is a great failure. This beautiful prediction is also a great failure. A total failure. Glesher will stick to that. So let's, in order to appreciate the development of the standard model, let's actually take this seriously. Although it fails, and we can see immediately it will fail, let's pretend that it's good to understand how it works. So let me write down a gauge theory of SU2. So I have a doublet, psi is a doublet. As I said, psi goes into U psi. So psi stands for, I should call this, as said, for example, I've said I'm going to call this a lepton doublet, and then we're going to call this a quark doublet. So psi would be a quark doublet or a lepton doublet. And then the Lagrangian is simply by analogy of SU2 is the same as we wrote in U1. It will be I psi bar gamma mu d mu psi. We would write the mass term and so on. I'm not interested in the mass term, I'm interested in interaction. What is the form of d mu? This is something that you have learned. Because of the symmetry, it must be one and the same coupling constant. And where there was one generator in QED, now there will be 3 generators, and therefore there will be 3 gauge bosons. Agree. This symmetry, this Lagrangian is invariant under phi goes into U of theta phi, which is E to the I theta A of X now space-time, dA psi. This is very important. It's space-time dependent. Of course, it is invariant as long as I specify how A mu transforms. And it's convenient to introduce this quantity, TA, A mu A. Actually, it's convenient to, I'm sorry, something got in my, I had to read it. Let me introduce the quantity and call it A mu A. This matrix is useful to, because then I can write immediately how A mu A transforms. It transforms into U A mu, u dagger. Notice as a difference from the photon, it's actually transforms non-trivially. No, there is no A mu A. Nobody corrected me. This is not good. You are not here. Are you following me? I made a mistake. I'm summing over A, obviously. You agree? I have summed over A. Repeating the index is summed. Okay, I could have written, but I'm always doing that. No, there is no sense. We decided that as usual. So there is no A. I apologize. What else, what is missing here? It's not complete.
U d mu.
U dagger, because it's a gauge field. Oh, sorry, that should be in red because we are talking about the, I'm sorry, minus I over G, U, thank you, d mu U dagger, very good. This is what you guys have learned, right? Apparently you have done Yang-Mills.
Yes.
Good. This is the piece, this is the analogy, just like the photon. This, of course, is new. Well, I can write it also in the case of the photon, but this would be invariant, nothing would happen here. It's new in a sense that they transforms. By the way, when I break it down into components, I will find out that A mu A goes into A mu A plus epsilon A B C theta B A mu C minus 1 over G d mu theta A. I have a complete analogy, okay? This piece is photon-like. But this is, of course, a fact that there is a new fundamental property that gauge boson in Yang-Mills carry internal charges, okay? They transform under the global symmetry. They are not neutral. How can they be neutral? They carry in an index. Obviously, to each generator, there is a different A, and that makes all the difference, okay? Therefore, when I write down the Lagrangian, I must introduce the analog here, which you know, and this is the analog of the, it's good that you know, so that it simplifies my job. Instead of one, electromagnetic field, now you have 3 SU2 fields. We can write detailed properties next time. It is not crucial. At the moment, what I wanted to emphasize is this. The beauty of the gauge principle, that I have the same universal interaction that I had in U1. Even more spectacular, because of SU2, everything is interconnected, and unlike U1, when charge was arbitrary, in U1, if you tell me that there is a charge, you observe tomorrow a particle with a charge 1 over, I don't know, 3.427, or a charge with 0.32, whatever, I can include it, not in SU2. In SU2, because of the commutation relations, just like spin, everything is quantized. This is very important. Okay. So look how this interaction looks like. So we have, in other words, the interaction will come. So when I write the piece, so interaction, we want to now develop the interaction. It comes from I, psi bar, gamma mu d mu psi, which has a kinetic piece. I'm not interested, plus I, and then I had, where is my covariant derivative? It's minus I. There is G, psi bar, gamma mu, TA, A mu A psi. This is interaction Lagrange. So I get that interaction Lagrangian. You see there is G, there is no G over square root of 2. It looks like this. Psi bar, gamma mu. You know the Pauli matrices, so I can immediately write. There will be 1/2 coming out. TA is sigma A over 2. So what do I have here? Please make sure I don't make a mistake. There is A mu 3. There is A mu 3 with a minus sign, right? This is Pauli matrix 3. There is, the other tools are off diagonal. So there is here 1 minus I A mu 2 plus A mu 2 psi. This is now the explicit form of the interaction. Let's remind us, the psi has an upper component. It can be an up quark or a down quark, but any doublet I can call up and down, which then becomes G over 2 U bar gamma mu U minus D bar gamma mu D A mu 3. I have taken the diagonal part out, you agree? Plus G over 2. Look at the off diagonal part. There will be U bar gamma mu D A. Why don't I write the A mu 1 minus I A mu 2 plus G over 2 D bar, the Hermitian conjugate U, A mu 1 plus I A mu 2. We agree with this? Notice what I have achieved. I have achieved that up becomes down, as I expected. So I should give the name to this gauge boson, and the name is W mu plus or minus is defined as A mu 1 minus plus I A mu 2 over square root of 2. I put a square root of 2 just to keep the normalization canonical. I normalized 1 and 2 in a certain manner. I want to keep the same normalization. These are obviously W plus or minus charges, because look what you get then. Then immediately you say the G over square root of 2, you get U bar gamma mu D, W mu plus Hermitian conjugate. So for example, this would be, in particular, this would be G over square root of 2, nu bar, gamma mu electron, W mu plus. Precisely what the W boson will do. W boson takes a neutrino and makes it an electron so that he can give me a beta decay. Now I could really, so what could happen in a beta decay? Let me maybe do it like this. This works. SU2 will immediately reproduce the weak interaction. So down quark will enter. That was my neutron. It will become an up quark. It emits a W. Down quark emits a W, becomes an up quark, goes out. I call it a proton. W goes out. W plus entered. Sorry, W plus entered. So what went out is W minus is going out. And that means I can get an electron out and neutrino enter. So that means that I have an interaction of the form U bar gamma mu D E bar gamma mu nu. This is my, proportional. We'll worry about details later. Reproduces beta decay. The first step works beautifully. I can say that my SU2 gauge theory could be a candidate theory. I have a W boson. I have to understand, of course, the mass of the W boson and so on and so forth. This is what the course is going to be all about, but I'm on the right track. There must be also the photon. I want to reproduce the real world. The only candidate for the photon is here. You agree? This is the neutral guy. So I'm predicting a photon. I predicted a W boson from my structure. I also predicted a photon. So besides W, there is also the photon with an introduction. Unfortunately, photon is A mu3. Unfortunately, I'm saying this beautiful charge is quantized, but it's wrong because I have an interaction A mu. I can again write with every fermion, it will have an interaction of gamma mu T3 times F. I can write it in a very nice form because it's diagonal. This is this fact that it's plus a half or minus a half. This is T3. You see, this is why it's A mu U bar gamma mu U minus D bar gamma mu D normalized with 1/2 as an outside factor. That's the form of the T3. So there is a photon. It has a universal interaction. The charge is predicted, but it's wrong. Okay. Charge, once again, I write the charge is quantized. The trouble is that it's wrong. And you see, there is no way we could be right because of the difference between quarks and leptons, right? There is up and down quark. If I think of the quarks, the charges are 2/3 and minus 1/3, whereas in the leptonic multiplet, I will write once again, the charges are 0 and minus 1. I should give up SU2. I have a challenge anyway to face. By the way, electromagnetic interactions are parity conserving. So really, in order to reproduce the weak interaction, what I should have said, that the doublet must be left-handed. This is very important. Why? Because if it is a left-handed, then there will be a left-handed and a left-handed particle here. For example, left-handed neutrino, left-handed electron, and so on. And I will have a V minus A theory, but in order to do that, my quark and lepton doublets must be left-handed. But if I do that, I get immediately a prediction from here that this is also left-handed. So I have a double problem. Not only that the charge is wrong, I have a serious problem. Weak interaction is left-handed, follows that electromagnetic is also left-handed. Or if one is right-handed, the other one is right-handed. If both enter, both will enter. So SU2, another amazing example of that era. Today, if I have a problem, I will immediately enlarge the gauge group. But Glesho took 3 years, banging his head against the wall, trying to see what happens. Okay, this is in 1960, he writes the thesis, and Glesho says, no good. He gets PhD at Harvard. He goes to Copenhagen to become a postdoc. The next stage is in 1961. Glesher again takes the courage and says, I must enlarge the gauge group. He says G minimal is bigger than SU2, not equal. I'm not going to give up. Thank God he didn't give up. But it also tells you how much he was in the dark, how much people struggle before they have courage to say things. 3 years, Dirac to say that there is a positron, trying to figure out what in the world is going on. When you read today, it all looks very simple, okay? You would imagine, oh, a brilliant person could have done this, in a span of, I don't know, 2 weeks. In 1961, so what will be G minimal? What is the G minimal? There is no option. If I want it to be minimal, it's very pragmatic. He says, I'll just add the most minimal thing in the world. I'll just add another U1. That's what I'm going to add. It's sort of, in a sense, it's embarrassingly simple, no? It's like the famous Einstein cartoon. There is a New York Times Einstein cartoon. Einstein at the blackboard writes EMA square. It's a beautiful cartoon. I don't know, I should find it and send it to you. E equal MB square. He's scratching, he says. Then he writes E is equal MC square, and you can see him jumping happily around. I got it. In some sense, this is the approach, okay? The first idea was brilliant, to see it as a gauge theory. That takes courage and insight and so on. This next step is kind of obvious, you agree. What does that mean? That now there are 4 gauge bosons. There is an immediate prediction. Glesher says there is W plus, there is W minus, there is a photon, but there is also, that you knew, if there were weak interaction, there is also a Z boson. And the Z boson is neutral. It must be neutral. I just added U1. I already had a neutral guy associated with T3. Now I have another neutral guy. He predicts the existence of what I call neutral currents. He, of course, knows that this particle must be massive. It has not been seen. So, of course, MZ, you say, is much bigger, once again, than the mass of the proton. And you say, I expect it. He doesn't know how big it is. He can't tell you what the number is. He said, I expect it on the order of MW, but strictly speaking, I don't know. I should put a question mark there. Okay, Glesher says. I have to understand what the mass is. He doesn't do that. That will be done by Weinberg many years later. Notice an interesting thing here that I will say only a few things, and then we will start tomorrow systematically. We will also go through the massive gauge field theory. It's called the Proca theory, derivation of the propagator, so on, the properties, the spin study, the polarizations, polarization tensors, and so on. We'll be oscillating. The lecture is often oscillating from very maybe dry, technical, and boring stuff, and then I'll try to give you some physical insight, both from the point of view of the past and the future. I'd like to bring the past into present to help us. One of the reasons I do that is not just because of my gray hair, it's to help us to think where we should go next and how. In that sense, past can be useful. There may be a message there. You never know. There may not be. But that's why we study history. And sometimes we learn and sometimes we don't. So what I can say here, something nice, I can ask you, what do I mean that the theory is SU2 cross U1? So let me see let me tell you what I mean by SU2 cross U1. There are 3 generators here that I call TA. And there is a generator here that I called y over 2. Y over 2, just some historical. And not y. There is a coupling constant G associated with SU2. There is a coupling constant G prime. What I mean by SU2 cross U1 is the fact that hypercharge commutes with TA. This is very important. Of course, TA and TB have the usual SU2 commutation relations. I should be finishing soon. I'll try not to abuse your time, but sometimes you will forgive me if I go a few minutes longer to finish the line of thought. So I have a question for you, a fundamental question. Could hypercharge be electromagnetic charge or proportional? Is that possible? See, I have no idea what is hypercharge. I call it hypercharge, okay? Just to give it a name. But I'm asking you, can this be electromagnetic charge, really? Before even working out details?
No, because
Yes, please, yeah.
The Q electromagnetic is proportional to T3. And they don't commute.
No, Q electromagnetic is not proportional to T3. That failed. Oh, that's very important. It cannot be. I know, sorry, okay. Say to the end, okay, maybe we tell me more.
I was just gonna say that T3 does not commute with all of the other generators.
The T3 doesn't commute with other generators, but T3 doesn't have to commute with other generators. No, okay. This was a question number 1. Question number 2. Can T3 be proportional Q electromagnetic? But here we know the answer, you agree. I can answer it immediately. Here is no. We saw that it doesn't work. You agree? That already I answered. But here I'm saying, can Q electromagnetic just be hypercharge? Nothing to do with T3. So forget T3. I'm asking a hypothetical question. Could? So in other words, I gave an answer immediately. This is obvious. So let's write like this. Answer 1 in red. You see, that would mean that Q electromagnetic, the question 1, would commute with TA. That's another extreme possibility. One is that electromagnetic charge is just T3, the other that it's outside. This would imply, however, that Q of the up quark must be equal to the down quark. This is what it means to commute. Because if it's outside, then it cannot distinguish the members of the doublet. So every up quark, every up particle would have the charge. For example, Q neutrino would be equal to Q of the electron. And this is wrong. The answer is no. No. Which tells us we will stop here. We had a fundamental prediction now immediately of the standard model, of the Glashow's work, that Q electromagnetic must be a combination, some combination of T3. I'm going to take coefficient 1, some combination of hypercharge. I don't write the coefficients here because this is arbitrary completely. Because it's arbitrary 1, it's any number I wish. So this way I can normalize it already any which way I want by using my Frieder here. I've just found out, this is very important, I just found out that I have an electroweak theory. If I wanted to have a gate series of weak interactions, I cannot have electromagnetism outside. They must be unified. You see, charge lives a little bit inside SU2, a little bit outside. It must do that. Okay, this is why we call it electroweak. Well, not truly unified, okay? Unified, I will put in quote, because there are two gauge couplings. Unified would be real name if G prime was equal to G, but there is no reason for me. I cannot assume that G prime is equal to G. However, there is some kind of unification in a sense that the photon, in other words, lives a little bit in SU2. In other words, photon is not A mu 3. It's some combination, I don't know, of A mu 3 and some combination that we have to, or what I call B mu. I forgot to say here, there are TAs and there are associated photon generators A mu A associated with the hypercharge. And here there is a boson that I will give a name B. And that's enough for today. It's time to stop. So as you can see, what I've done already in the second lecture, the rest of the course will be developing the theory. And you will see how at every point the theory anticipated experiment will get a plethora of simple, beautiful, clear predictions that will culminate with the Higgs mechanism and the theory of the origin of mass. Okay, the standard model will grow to be much more profound than the way it started. Okay, but you can see already today where I'm taking you. And I'll try to give you from time to time an outline of where we are going. I do it this way because I like to be taught this way, not just to learn without knowing where we are going. Questions, please. There could be something that was, you know, please. Even if I left you behind, ask any question as silly, as fundamental as. Without questions, I won't know if I'm going too fast or too slow, or I'll sort of have to play it by ear. Okay, it seems, I hope I was clear, and that at least the message you got, that we have just built the unified theory, that we have to understand why we built it. Okay. Then I see you tomorrow, right? Oh, by the way, I have a question. When you, what do you get when you receive the broadcast? You see my notes? I don't have to send them separately? Would you like to receive them separately, my notes?
Yes, I think we would like to receive your notes if possible.
Yeah, okay. I'm gonna ask someone, I don't know, in our section to help us who have a joint email address. Okay. Somehow when I'm sending from the GoodNotes that I'm using on my iPad, I can't send it to you individually, but I'll try to find a way. I think also this is useful. This is a great thing about the Zoom, that you can have notes. You don't have to go through the broadcast. Okay, we'll figure that out. Okay, very good. I see you tomorrow.
Thank you.
Thank you.
Thank you.